because we need to synchronize the live stream. Okay, so we need to be quiet for a moment. I mean, doing the talk preferably as well, but already now. And then I think once I get the message, we are good to go. But I think we're good to go. Okay, so welcome to our seminar today. So this is the first time I think we do it in this way, because this is a dual seminar. So we're actually attending two seminars at the moment for the price of one. One is in person with Steffen here, Professor Zschaler here in person giving a seminar at the University of Leicester. The other one is live streamed as part of the GReTA seminar. This is the seminar on graph transformation, which I'm sharing as well together with two other people. And so it goes out basically at the same time as an online seminar, which is also recorded on YouTube. So if you're interested, you can also look at the video later. The talk today, as you can see, is about sort of model-driven development, compositionality, and of modeling languages and so on, which is of course related in many ways to some of the things that we teach here as well. So we obviously in my module, but also in generative development and an Atos module on cloud, agile cloud automation. You probably have seen some of the concepts. So this is obviously research oriented, so it will go much further than that, but it's basically the same general problem domain, and then elaborated in more sort of advanced theory. So I'm very happy to have Steffen here today, who is an expert in this, as you can imagine, leads a network on this in the UK of basically researchers from lots of different universities doing research in model-driven development, and obviously has a lot of experience himself in his own research. But I'm sort of not going to enumerate all of that. I just hand over to him, and he can tell you that he's doing. Okay, so please.
Thank you, Raiko. And welcome from me as well. Welcome to people online and to everybody in the room here. To start us off, I'm going to do what I do with my students back at King's as well when I have a first lecture with them, which is to say, if you're sitting in the back row, then you're too far away for me to see you, and therefore you're too far away to have fun. But there's lots of spaces in the front rows. So if you want to sort of all come one row or two rows forward, then we're going to have so much more fun as a group. Off you go. I'll give you a moment to do this. This is the active part. If you're in the back rows, come forward. There's spaces here. I don't bite. Excellent. Very good. And if you're just arriving, don't even go to the back rows. Excellent. That's so much better. It feels so much more cozy right away. Okay. So today's talk is about composing executable domain-specific modeling languages, and I'm going to try and explain what the bits and pieces are. I have a rough idea, I think, what I can expect in background knowledge from the people online, but to get a sense of where you are and how I pitch this, can I sort of just get a raised hand from people if you know what a domain-specific language or domain-specific modeling language is? Okay, do art or proud. Okay, cool. Okay, that gives me an idea. Can I get a sort of a raised hand if you know what a graph transformation is? Okay, well, we'll start from scratch. Let's see how we do. Okay, so domain-specific languages. I'm going to assume you know what a programming language is. A domain-specific language is something a little bit like a programming language, but you can't do anything you want in it. You can only use it for problems in a particular problem domain. So you might have a domain-specific language for banking problems, and it allows you to talk about things in the banking domain very precisely and very efficiently, and to then produce programs out of that that can run and can be executed and you can do stuff with. But it doesn't allow you to talk about gardening or childcare or healthcare or anything like that, because that's not what it's for. Okay, and that's a good thing, because by narrowing the scope of our language, we make sure that we can provide much more dedicated and bespoke support to the users of that language. So developing applications and solutions in that particular problem domain becomes much more efficient, and the applications that we build become more robust, because we have sort of standard patterns of how we solve problems in that domain, and we can encode them into our language and into the compilers or interpreters for the language, so we don't have to worry about them again and again and again. Okay, so that's sort of the key idea of these domain-specific languages. We're going to come to the graph transformation bit a little bit later. Now, if we're having these languages, and we want to have all of these different languages for different domains, we really carefully have to think about how to build languages and what are the key bits of a language. And that's sort of where my talk starts today. Okay, so here is a quick picture that sort of shows what are the key components of any language. And that's true for programming languages, as you might know them, but also for domain-specific modeling languages. Okay, and there are three there. We've got, is this visible just about? We've got the abstract syntax. That's the set of concepts that exist in our language, the things that we can talk about and how they interrelate. Typically, certainly in the MDE world, when we build these domain-specific modeling languages, the way we write this down is by writing down a class diagram that has sort of classes or boxes for the actual concepts and uses associations or references for describing the relationships between those concepts. That's a fairly abstract thing, but all it gives us is essentially a data structure that we can then use to store models in that the user has written in our model in our domain-specific language. Okay. What it doesn't give us yet is knowledge about what that language looks like and feels like when the user interacts with it and uses it. That's here in the concrete syntax, drawn this the other way around from what I usually do. It's in the concrete syntax. So the concrete syntax is about what does it look like on the screen? How do I interact with that language? How do I edit things in that language, etc. Okay. And in fact, in principle, though we're not going to touch on that today, we could have multiple different concrete syntaxes for the same abstract syntax. We could say have a diagrammatic syntax and a textual syntax, and that can be useful for different users. So far, that's just syntax. That's just, I can write down stuff and this is what it looks like. It could mean anything, because computers are really dumb. Right? As far as they're concerned, it's all zeros and ones. They don't know what these things mean. We've got to be explicit about what we want these constructs to mean. And that's where this bit over here, the semantics of the language, come in. Okay. And that's something that we want to look at a little bit more today. So let me just sort of briefly add a little bit of detail. So here's some examples of what we could do to produce concrete syntax. And here, we're going to talk about how we typically describe the semantics, so that is the meaning of these languages. Okay. We describe them by providing simulators, by providing analyzers, by providing code generators, interpreters, possibly debuggers, all kinds of things like that. Okay. There are different techniques for describing semantics. Today, we're going to focus on something called operational semantics, which is essentially, if you will, an interpreter of my language. Okay. And as you see in the title of the slide here, but also the title of the talk, I'm not just talking about domain-specific modeling language. I'm specifically talking about executable domain-specific languages. And the key here is that they come with a form of semantics that's not just about analyzing models, but that's about actually executing them, about making them do something. Okay. And so operational semantics, what we've just talked about, is one way of doing that. And so if a lot of the focus of the talk will be on this side around semantics today. Okay. So in this sort of world of executable domain-specific modeling languages, what we're trying to do is we're trying to provide the syntax of our language, and we typically have good declarative ways of doing this nowadays, but we're also trying to provide declarative descriptions as much as possible of the semantics of our language in ways that fit into a reasonably generic framework so that we don't have to build completely an interpreter or a code generator every time for every new language we're building, but we can focus on the essence of our semantics and get the rest essentially for free. Declarative is good because rather than imperative, right? So we could write our semantics imperatively. We could write an actual interpreter, write little classes and methods with code in them that say, this is what you do when you see this statement in the language. This is what you do when you see this other statement. That's typically how many interpreters for interpreted programming languages are written. But declarative is good because it has the potential to allow us reasoning, and as we'll see, it'll allow us a level of composition of semantics that's a bit more robust. It's a semantics, it's not done because it's not imperative, it's a semantics, but not yet an interpreter, because it doesn't talk about how things are scheduled or anything like that. It just sort of gives you the general rules. And then there needs to be a machinery that underneath that knows how to interpret those rules to give you an interpreter and to give you other tooling. Luckily, there is this idea of language workbenches that we've developed in the MD community, which allow us to build new domain-specific modeling languages quite efficiently. And the whole idea there is you give me a declarative description of your language, and from that, I have machinery available that can either generate you the full infrastructure for that language, or that knows how to interpret that declarative description to give you the tools to use that language. That starts from editors all the way down to potentially executing things. One such language workbench that we're going to very briefly look at just in some screenshots on the slides here is the GMOG Studio, which is built in France, which allows you not just to declaratively define the syntax of your language, but also the semantics. And from that, you get a whole debugging framework for your language. So let's look at this brief example. So this is an example language. You don't have to be able to read all the details here. We're not going to touch on this particular example. Again, it's just to give you a quick idea. It's a language that allows us to talk about banking and to write little programs that are about how people interact with their accounts, how they withdraw money, add money, things like that. So it's got a set of very simple statements. And we've got at the top here, we've got the abstract syntax in a form that we call a meta model, which is, as I said, is a class diagram. You see boxes here for the various concepts. So a banking program has a script, which is the actual program. But then on the other side here, it has some structures that actually represent the state of the bank at this point in time. So we've got the bank has various accounts, as a manager has clients, and so on. And the script can have different types of actions that you can actually perform in sequence. Okay. And then there's a concrete syntax, which in this case is visual, which we see at the bottom here, which represents a particular situation in the world. Okay. So we see the script here on the left, and then we see a particular configuration where we have a manager that manages a particular client. That client doesn't have an account yet, which is why there is a create account statement. That's the first account statement in our script, and so on. Okay. Now that, as I said, that's just standard GMOG, standard syntax definition for our language, and we can write models, but it doesn't then have the semantics yet. The semantics are then described using graph transformation rules. Now, these are graph transformation rules here in a particular graph transformation system called Henshin. Let's look at some examples. Let's look at this rule here. So this is the rule that says what happens when I hit a create account statement in my script. Okay. So on the left-hand side here, it says if I can find the script and the current statement in that script is a create account statement. Then that create account statement will have various information in there, and in particular, it hasn't run yet. And then on the right-hand side here, we go, oh, and if I can find a bank that has a client that where the client name matches the client name in my create account statement here, then I'm going to create, that's the green stuff that with the little create labels that says, what are we going to do? What's the result of applying this rule? Then I'm going to create a new account for this client inside this bank. And I'm going to give it the ID that's given in this create account statement here. But I'm only going to do this if there isn't already an account with that ID. Okay, because if two people share the same account ID, that's a problem. And the other rules in similar ways describe the remainder of the semantics of this language. Is this clear so far? Do you have a sort of a bit of an internal image of what this is doing? This is all we need to describe our language. From this, in Gmorph, we can automatically get a whole debugging environment. Okay, so this is now, of course, didactically badly a different example. It's the example that we are going to carry on with. There is a slightly different language here. The rules for that are just too many to show. But you see the model, you'll see the model up here. In the bottom left corner, you see a trace of how you've debugged through your thing. So each dot here is a state of the model that we've looked at, and we can go back in time to previous states and to explore what happens if we go down a different path. And in the bottom right corner here, we see we see what's currently possible, what we can currently do, what steps could we currently take, and then we can sort of explore our way around this. But also we can, edit this model at will, and we can work with it and explore it in different ways, right? So we've got sort of a standard view of the current model state. That I've said, I think, all of this. Oh, and then here, in fact, we also have some strategies that allow us to sort of narrow things down a little bit, because that list here with available next steps can potentially grow quite large, right? If I've got things that can happen concurrently in my system, then that list can grow quite large. But here we have some strategies that can allow us to say, actually, I'm only interested in particular types of steps that I want to take, and I can narrow this down. So this is quite powerful and quite nice as a way of developing languages and developing tooling for languages, because we can just declaratively describe everything about the language and then get quite a lot of tooling for free. So hopefully that will help motivate a little bit why we want to use this sort of approach where we're using declarative sort of class diagram style models for capturing the syntax of our language, and graph transformations for capturing the semantics of our language. What I want to talk about a little bit further down the line is some additional things that doing this enables in terms of reusing language components, recomposing language components, and so on. And so in order to do that, let's look at our example in a little bit more detail. And we're going to carry on with this example here. So let's look at that in a little bit more detail. So here is the meta model for that example. So that's our abstract syntax. Now, this example is a language, a toy language, because that means I can fit it on a slide and I can explain it reasonably quickly. It's a language that allows me to represent production line systems, fairly simple production line systems, and to describe what the behavior of those production line systems will be, so that I can step through that, etc. Small as it is already a fairly interesting case study, because it essentially is a fully concurrent language. Many things can happen at the same time in any given model state. And it's interesting to explore what sort of the minimal ways of describing the operational semantics for this are, but also how we then make those semantics accessible through a debugger, etc. Right? So in this language, what do we have? We have a plant, which is our overall system. And in there are various elements. In particular, there are machines, things that do stuff. There are containers, which is if we've produced stuff and it's waiting to be handled, that it needs to go into a container of some sort. In particular, containers can be trays or conveyor belts. And there's users who eventually pick stuff out of these containers and go away and sell them or whatever they end up doing with them. But at that point, we kind of don't care about the things anymore. And then obviously there's what we're actually producing, which are these parts. And in this very simple language, we actually have a very limited set of very specific parts that we're going to manage, as well as a limited set of very specific types of machines that we're going to allow in our models. Okay. And then down here, I've just sort of shown some icons that give you the concrete syntax of how I'm going to visually represent instances of these various bits of abstract syntax. Okay, so a user will have this little icon here, a gen head machine, which is one of these here, which is meant to be a machine that produces a new hammerhead, will look like this, and so on. Okay, so with these syntactical structures, we can produce models that look like this, for example. Okay, so this describes a specific configuration of a production line system where we have something that produces handles here, a machine that produces heads. They go onto conveyor belts, which eventually put them into this tray. And then there's a machine that sort of will hopefully pick out a handle and a head and put them together and produce a hammer and stick them on here. And eventually somebody goes and picks those up. Okay. The semantics of this, so saying what this means and how this behaves, again, we're going to describe using graph transformation rules. And here is an example of such a rule. I'm not giving you all the rules. It's written in a slightly different notation. It's a slightly older example. We'll see a version of this in Henshin in a moment. This is the rule for the machine that produces hammers out of heads and handles. Okay. In the Henshin notation that we saw, I have this gray and green and red bits. Here I'm showing the same information just split into two parts. Okay, so the gray bits, the things that aren't changed, are the things that are both in the left hand and the right hand box. The things that get removed are the things that are only in the left hand box, not in the right hand box. The things that get created are the things that are in the right hand box, but not in the left hand box. Okay. So what this rule does, it goes and says, okay, if I have one of these machines that assemble hammers, and there's a tray attached to it, and probably an conveyor belt attached to it, and in that tray there happens to be a head and a handle, what I'm going to do is I'm going to remove that head and handle, and I'm going to produce a new hammer, and stick that hammer onto my conveyor belt here. Okay? And then you can imagine there's a rule, for example, that says what a conveyor belt does. Well, it says if there's something on me, I'll sort of transport it on into whatever tray is next to me, and so on. And there's rules for all the other machines. Okay. Well, for now, we'll ignore those sort of bits at the bottom here. They're not hugely relevant to the talk today. Okay. Now, this is nice. This tells me how the production line system works. One thing that I might be interested in is how well it does what it does. Okay. How long does it take to assemble hammers on average? These sorts of things. Okay. Now, the beautiful thing about this mechanism for operational semantics that we have here is we can actually capture this sort of information by just attaching a little extra object to our system and to our and catching that in our operational semantics again, which will observe this machine and record information about what it was doing. Okay, so we add a little extra element here, attach it to our machine, and now in our semantics rules, we also have this element. And what we do is we say, oh, last time we did this, it took so and so long. Okay, this means in our graph transformation system here, in our model, we have to have a notion of time that we can track, but that's easily done by having some additional variable that essentially just sort of tracks time in some way and gets sort of updated here. And in fact, that happens. Where does that happen? There, up there, it's sort of annotated there. So this particular graph transformation mechanism here has an inbuilt notion of time, And at the top of the rule, we kind of say what the delta T is for the rule execution. But the important thing is now this object here now keeps track of how long it takes this machine to do stuff. Okay. So we have an observer that observes the non-functional properties of our system. And that means we can now write specifications over that or do analysis over that to sort of go, okay, can we just record all of those values over time and tell me what the average response time is, or what the maximum response time is, or the minimum or the 95th percentile response time, and so on. Okay? Which is a very interesting property for us when we design systems. Now, of course, I said we have these domain-specific languages. So we want to build languages for other domains, right? We might want to, for example, build a language like this, which talks about how passengers are processed at airports. Okay, so we have an airport here. There might be queues of passengers. They're passengers of particular planes. And then there might be check-in desks, and the passengers can queue at the desks, and they can queue at the planes, and so on, right? So then we've got, again, have a visual syntax to represent the various bits and pieces. And so with this, we can write models like this, where we've got sort of a number of check-in desks set up, and we have queues in front of them, and we might have passengers in those queues as well. And we write operational semantics that says, how does this work? Right, well, if there's a queue that has a passenger in it in front of the check-in desk, and the check-in desk is open, then the passenger can get processed at the check-in desk, and that moves them into the queue in front of the plane, virtually, right? We know there's more going on, but as far as this model is concerned, we kind of just dump the passenger in the plane queue, okay? Now, of course, we might very well actually want to ask the question of, so how long does it take for a passenger to get processed? How long do they spend in those queues? How long does it take for them to be processed at our check-in desks, right? Well, we know how to do this, don't we? We add an observer object to our abstract syntax. We add it into our rules. We say, okay, now we have an observer object at our check-in desk, and we observe how long it took. And then in our model, we add those observers everywhere as well. Okay? With me so far? Good. Notice a problem? Okay, it doesn't actually observe the queues. So if I want to do observation over the queue, then I have to build a slightly different version of this model, and I've got to put an observer on the queue. That's a valid point. The problem that I'm after today is we've already done this, right? When we were doing our production line modeling language, we did essentially exactly the same. And now we've done it again. And if we build another domain-specific modeling language tomorrow, but we want to talk about these sort of timing properties, we've got to do that again. We've got to again add these observers. But actually, the extension of the abstract syntax and our operational semantics, they follow the same schema. Right? For the same property, we do essentially the same thing every time. So why do we have to reinvent that wheel again and again? Wouldn't it be nicer if we could specify it once and then weave it into the language that we're interested in? Okay, so that's where the composition bit comes in, and that's where it's actually really useful that we've written our semantics in this declarative manner. So let's look at how we can do this. So what we do is we write an abstract specification of what we mean by this time thing. Okay. And it turns out we can't just say, well, we need an observer that records time. We've got to provide a little bit of context with it. We've got to kind of say, what is it observing? Because as you've rightly noticed, right, if we're interested in observing the time it takes in queues, that looks quite a bit different from observing the time that sort of a machine or a check-in desk takes to process something. So we've got to provide a little bit of context to say, what is it that we're observing? And in this example, the kind of context that we need to provide is what's in this light gray box here. Okay, we've got to kind of say, well, there's something that we're going to call a server because it serves requests of sorts that has an in and an out queue, and in those queues there might be requests, and then we attach this observer object to our server. Okay, and I've put this sort of dashed rectangle notation up here to kind of indicate that everything that's in that gray box is kind of a parameter of this meta model here, of this abstract syntax. We're not saying there's going to be actually a server. We're just going to say there needs to be something that can play the role of the server. There needs to be something that can play the role of a queue. There needs to be something that can play the role of a request. And maybe you can already kind of see how that might map onto our production line example, or how that might map onto our airport example. Okay. And then, of course, we've got to also do the same thing for our rules. We've got to say, well, we've got to have these parameterized rules now where we say, this is the sort of pattern that we expect to see in a rule. And this is how we systematically extend that rule to also do the observation. Yeah. And so now something really interesting happens. So we have our language. Let's just look at the syntax of our language that we've just seen here. And we can kind of say we can pull out that interface bit, just the bits that are in the gray box. Okay. And we can say, well, okay, that's an interface for this because everything that's in here occurs down here, but there's a bit more down here. Okay. But now we can say we can map everything that's in here onto something in the syntax of a concrete language that we have. Okay. And if we can do that, then it turns out that we now have a mechanism to weave the whole thing together and say, okay, in this rule here, we're going to systematically replace the server with whatever we map server to over here. And so we're going to attach our response time object to this assemble thing. Actually, that I'm kind of inconsistent. This should go to assemble. Apologies, that PowerPoint tricked me a little bit. So this arrow, assume this arrow goes to assemble here rather than the generic machine. And then we attach that here. Yeah. Now, of course, and we're going to get to that in a moment, of course, we can't just willy-nilly do these mappings here. Right? We've got to do these mappings so that the structure that we're mapping to on the other side satisfies or matches the kind of structure that we were seeing here, right? So if there is an in link between these two objects, then whatever I map this to and whatever I map that to also has to have that sort of connection. And I need to be able to map that connection because otherwise it all breaks, right? And that's kind of the purpose of having this interface structure here. So that gives us a pattern that we're looking for in our concrete language. Okay. And we do the same for our rules. Actually, no, we do the same. First, we do the same for our airport language as well. So we can do this now for different languages, and we get this mechanism that now gives us the extended syntax for the airport language. And then we can do the same thing for the rules as well. So again, we can pull out our interface rule, which is just the bits that we want to map. We find that pattern in the other rule, right? So this is reasonably straightforward, hopefully. And then we can sort of push out this composition here. That is our composed rule. And we can do that for our other language as well. Okay. Now, again, those of you who know graph transformations and this sort of thing will probably already have gone, oh, there's something wrong in that example. We'll get to that in a moment. Okay. What I want to show you first, hopefully, is that you can actually do that in a tool. So let me see whether I can wrangle my computer sufficiently. But this is, I think, is where I need to briefly stop sharing and change my setup. Give me a moment here. I want to duplicate these. Yes, changes. Okay, so here Oh, and I'm not sharing it. Yes, I need to share again. Thank you. Share screen. Share screen. Share. There we go. So here, you minimize this a little bit so it goes out, gets out of the way. Where are you going? Not going up there. Thank you. Okay. Right. So here I've got sort of my development environment. Here I've got my development environment, and what I have here is a textual representation of that abstract syntax for my production line system. Okay, it's not, I haven't shown it as a diagram, but it's the same thing, right? I have classes here, which are the various concepts. I have, for example, this machine class here, which has a conveyor and a tray connected to it. I have these conveyor classes here, and so on. I've got all the various bits and pieces here that we also saw in our meta. Okay. I've also got a set of sort of ancient rules. I've sort of simplified my life a little bit today. I've just written up one of them that show how a particular machine behaves. It's a different machine in this case, but it's the same idea. This is now written as a Henshin rule. So again, it's not the two-part thing. It's the red gets deleted, green gets added bit. We see, okay, we've got, let me actually make this a little bit bigger. If I can, yep. We've got our polisher machine in this case, which has an in tray and out conveyor, and it has a part that it finds there. It does something with it, and it produces a version of that part out there. Right? Henshin doesn't have time, so I can't quite show you the monitoring of response times. Well, what I can show you is something very similar. We might want to keep track of what has that machine produced, what has that machine done, right? It's a similar kind of property that I might be interested in. And again, I want to keep that separate from other things. So I've built a separate little language that just captures that. Assuming my computer is willing to cooperate, we will see this. So this is a very simple meta model for a language that just has this notion of I can track what a server has done. Okay, so again, I have a server notion here, which has an in queue and an out queue. We have this idea of a queue. A queue has elements, and that's all there is. But the server can also have a reference to output elements that it has made, that it has produced. And you will see I've got these little at interface annotations here throughout. That's the gray bit. Everything that has a little at interface thing is in that gray box that we saw. Okay. Everything that doesn't have that is outside the gray box. So that in this case is literally only this reference here for made things. That's the thing that we're going to add in to our modeling language here. Okay. And then we've got rules for what happens when a server processes things. Well, you know, it takes an input from its in its queue here, and it produces an output, but it also now tracks that it made this. Now we need to be able to merge these things together, right? We've got this language here, which is very generically describing the fact that we're essentially tracking what we've done. And we've got this other language here, which talks about concretely doing stuff. Yeah. And so what we can do is we can write this up. Let me forget about this bit for a moment. So we could basically say, actually this, we could basically say we have this server language, this generic language, which has this meta model and it has these rules. Let's forget about this bit for now. And then we can say now, we've got to, you know, remember in our square diagram, we had this mapping across that we had to specify, where we had to say which bits in the server language map to which bits in our production line language. And that's what we're doing here, where we're saying, okay, we're going from this server thing to the production line system, which has the PLS meta model here and the PLS rules, which we've seen in this diagram here. And then we're mapping first the abstract syntax concepts. And in particular, we're saying a server maps to a polisher. The input queue maps to the tray, and the output queue maps to the conveyor. And then we can weave those things together. And that's this step here where we say, now let's push these together. And what we produce is a combined meta model. Let me show you this here. I think I can open it up. Come on. A combined meta model. And what we say is in there, we have our polisher machine, which now has this made link. But notice it's now links to parts, not to elements. And I've got my rule as well. And let me show you that rule graphically. Come on. It's a difficult day for my laptop, clearly. I have my rule here now, which says, okay, I have this part which sits on the tray. I produce a part that sits on the conveyor, but I now also track the fact that I've made this part. Okay, and that just gets generated for me from these rules. Now, the interesting thing is, once I do this in the tool, I can actually start checking things about what I've written up. Okay, so if I try and say, I don't know, if I try and say this output queue should map to PLS tray, then it's going to tell me that that's not possible. That's not a valid mapping because it doesn't satisfy the structure of my interface model. Okay. Or in fact, if I say, well, I'm not going to tell you what input queue maps to at all, or what server maps to, then it should also complain. I think it doesn't quite. Oh, because it doesn't. I don't ask it to be whether it's unique. No. But yeah, but I can check various properties of this automatically at that point. You'll also see that I didn't actually have to say explicitly how the rule is mapped, because it turns out once I've given it the syntactical mapping, there is only one way of mapping the rule. And so it can automatically figure this out. If it can't, it's going to tell me again, and I'll have to provide additional information. Okay. So that's just perhaps a very quick demo that there is a way of supporting this in a tool. And conscious of time, I am going to move on with the presentation. So this is going to get a little bit more mathematical, not a huge amount. What's happening here is mathematically is that we establish something that we call a morphism between these graph transformation systems. And a morphism, you can essentially, that's those mappings, that's those point-to-point mappings. And the important property is that if I have a particular structure on the left-hand side, then my point-to-point, my element-to-element mappings must be such that I have a corresponding structure on the right-hand side. Okay. And now we've seen the diagram with the languages, right? We've seen that. And then all I'm doing here is I'm representing the same thing, but I'm calling these languages GTS 0, 1, 2. GTS stands for Graph Transformation System, because that's effectively what they are. A graph transformation system is a graph that says what are the types of things that can occur and how can they be linked together. That is what the meta model was in our language world. And it's a set of graph transformation rules that say, if I've got instances of these things, how can I change them? So that was our Henshin rules for our operational semantics. Okay. And then a morphism between these things is something that maps two type graphs, two of these graphs onto each other. And that maps names of rules onto each other, so that for every rule on the target side, we've got a corresponding rule on the source side. And then within those rules, it maps each element in the source rule onto something in the target rule. Okay, which means in particular that the source rule and the source meta model can be smaller than the target rule or target meta model, because I just have to make sure that I can map everything in the source to something in the target. But if there's additional stuff, then that's fine. Okay. And then there are a few little additional rules about what we can or cannot map, and we'll get to that in a moment. And then if we construct something like this, then mathematically we can produce an amalgamation of these graph transformation systems, which is basically composing all the rules together, composing all the type graphs together according to these mappings. And I've said this, I think, already. Now, what's interesting about these is there's some interesting properties that we want these morphisms, these mappings to have, right? And you can see, we'll just go briefly back to this. These dashed arrows down here and across, they're also morphisms. So they follow the same rules as the solid line arrows. The solid line arrows are just the ones that we have to write down. The dashed ones are the ones that we sort of get as a result of the composition. Now, these morphisms, they can be behavior reflecting, which means if I look at a rule on the right-hand side, on the target side of the morphism, then for every such rule, and in particular every concrete application of such rule, there must be a corresponding application on the source side. If I have that, it actually turns out that that holds for entire traces as well. So any trace, any sequence of applications on the right-hand side, then also has a corresponding sequence of applications on the left-hand side. That's nice. That kind of says, I've built my morphism and I haven't lost any of the behavior on the right-hand side. It's all still there on the left-hand side as well. It can all happen over there as well. Okay. I also want the same idea in the other direction, right? I want to be able to say anything that I've written down on the left-hand side can also happen on the right-hand side, because that's kind of the point of the composition that we're making here, right? We want to add new behavior into our language. We want to be able to do more with it, but we don't want to stop it from doing things either, okay? That way around is a little bit trickier, because as I said, there could be more happening on the target side than on the source side. There could be more in the rules, there could be more in the meta model there. So there could be more stuff going on. So the best we can achieve is, in fact, to say a morphism is behavior preserving if for every trace, so every sequence of transformations on the left-hand side, on the source side, there is a corresponding stuttering equivalent trace on the target side. And stuttering equivalent means this trace here might have additional steps in between. So there may be a step that corresponds to a step here, then it might do a few things, and then eventually it might do a step that corresponds to the next step over here. And then it might do a few things again, and eventually it might do a step that corresponds to the next step here. Okay? That's the best we can get. And the annoying thing is we can literally only check that on traces, because it's not the case that just because the rules happen to match up, the traces will also match up in that variant. But really what we want is for this to hold both ways. Is what we then have is this interesting observation property that we were interested in, where we're saying by weaving in additional behavior, we haven't changed, we haven't lost any of the original behavior, but we also haven't created any new behavior. But we're now also doing everything that we wanted to do on the left-hand side. Okay? And it turns out, so what we want is in particular that this sort of downward arrow, the GTS2 to this GTS hat thing, that's behavior protecting. And it turns out that we can establish a simple rule for that happening. Namely, if this morphism that we manually write is behavior protecting, and the one across at the top is behavior reflecting at least, then we can also get behavior protection on the one that we care about. This bit here obviously is a bit more difficult to verify, because we said we can only do it on traces. But again, it turns out that there's a special type of morphism which only extends rules with additional little bits. for which we can sort of show that this works, and that's the sort of interface mapping that we've seen. If we want to have other kinds of morphisms there, if we want to do other more tricky interfaces, then that becomes a bit more difficult. Now that's nice, but we've got to have this exact match of structures and exact match of behaviors. And that can be quite limiting. In fact, in our example already, it doesn't work. Okay, so we have this idea that we have these clan morphisms, so they're essentially structural correspondence on the meta model level. And we've got to have these exact rule morphisms between the individual rules. And that doesn't work, right? So here's the example sort of blown up a little bit again, where we say, well, okay, go to a different thing again, but it doesn't really matter which machine I go to for my server. But the tricky thing is that we've got out and in queues, but actually here we've got, so it's the same queue here, but actually here we've got different classes representing effectively the output queue and the input queue. And that's not allowed by the rules of the clan morphism, okay? Because we've got this thing, the only thing that we can map this to now is this general superclass here, which we can't map. If we map it to tray, then we can't map the output queue. And if we map it to conveyor, then we can't map the input queue. But if we map the queue to this thing here, then we don't know how to map these associations because they don't go to this thing up here. They don't go to only a specific subclass, and therefore we can't guarantee that they will always be present for every instantiation. And our morphism rules say, no, you can't do that. You're not allowed to do that. Okay. Similarly, for the rules, we have a similar problem. And in fact, that was, I think, in the example early on as well. Our generic rule only has one request that it finds in the input queue and then produces one request in the output queue. But our assembler rule actually takes two objects, two parts from its input element and produces one. So we're stuffed, right? It's all beautiful. I've told you this. You've spent sort of, almost an hour listening to me quite patiently going on about how this is all beautiful and works. And now I'm telling you, no, but it's too limited. It doesn't actually work. Of course, there's a fix, right? The point here is that these are technical issues that we're facing because we've got to have this very clear and clean structural matching. Yeah. But they're not actually meaningful. So we need to be able to adapt this, and it turns out we can. By saying, well, actually, we're talking on this, in this generic thing, we're not talking about a single graph transformation system, we're talking about a family of those. And we're allowing us to find the right one within that family. And then from that, we can then construct our square here and do our composition. And so, again, then do our usual checks at that point. And the important thing here is basically that this family is, I have a graph transformation system that I start from, and then there's certain ways in which I'm allowed to change this. And I can find, if I can find a path, a composition of a sequence of these changes to find a graph transformation system for which I can build my composition, then I'm good. Then I'm okay. So I can explicitly define the flexibility I allow by saying these are the changes I'm allowed to make. And that's me done. We've seen a few issues here and there, right? So there is a lot of research, the elements in here, so not everything quite fits together. So there's a bit of work left to do. In particular, I'd like to have more powerful verification mechanisms in the tool that I've shown you. And I think, we probably want to have conversations about integrating some of the work that you've been doing, which I think matches quite nicely into this. And that's me done. Thank you very much for your time, and happy to ask questions.
Thank you very much. I think we have to go out now because the next class is starting in 5 minutes or 3 minutes. So thank you very much, and see you next time. Yeah?
Sorry, did I slightly overrun on the time here? Apologies for that.
That's the problem with the online seminar, but
Yeah.
here we have the physical space.
So,
Thanks, Steffen. Can you guys find a computer and come back to the Zoom meeting so one could have a
I
discussion?
can stay on this. I can just take the laptop out because I'm on the
Yes,
laptop.
yes,
anyway.
exactly. Yeah. Sorry. Thanks for the talk. We just say here for a moment for everybody who still wants to discuss, you might need 5 minutes to rearrange the speaker.
On the laptop, and we can chat outside, I'm sure.
Okay. Yes, so for everybody who's on the YouTube stream, today we have a slightly special situation because the speaker is live on Leicester. So if you still want to discuss, please join the Zoom meeting. The link will stay open for at least another half hour. And for now, I will take the YouTube stream offline, and please follow our website for announcement of the next seminars. And thank you very much for attending. Until next time.